But okay, let's dive into it. Cool. So, circular function stuff. The general form of a circular function has much of the same terms that any other type of graph will have. Right? It's got some dilation factors, the a and the n term, as well as some translation factors, the h and the c in this case, both doing horizontal and vertical. As far as the general shape of circular functions, they more or less look the same as each other, where they have this sort of wave-like pattern. This is the graph of sine x. Sine will always start at a 0 and then immediately move up to its peak afterwards, whereas cosine will start at its peak and then move down from there. When I say start, I just mean what's happening at the origin, or at least at x equals 0, what's happening there. So there's a minor difference between those two. You can think of cosine as a slightly shifted forward sine, which is exactly what it is, actually, shifted forward by pi over 2. Like, for instance, if you're looking at these x-axis stuff here, this peak is located at pi over 2. And so because this peak is located at 0, you can kind of think of it as being shifted forward or backward by pi over 2, depending on how you look at it. Whatever the graph is, it's going to repeat in one cycle. That cycle is referred to as the period of the circular function and can change depending on the n term, which we'll have a look at. But for now, bare bones basics with no factors involved. The period is going to be 2 pi because that's how long it takes to go through the unit circle. One full revolution of the unit circle is 2 pi. So unless there's any dilation factors, that's going to maintain exactly as is. In the case of cosine, it'll go from peak to peak. In the case of sine, it'll go from middle, peak, middle, trough, and then back to the middle. As far as their heights, the heights will be determined by the amplitude, which will be a term at the front. Because there is no term at the front, or there's an implied 1 that's there, the peak and trough, so the max and the minimum, are both going to be at 1 and -1 respectively. Those are the basics for the graph of the circular function. As for how we start changing things, first we'll look at the dilation factors. So again, I mentioned the a here, right? A term at the front of the circular function. It's a y dilation. It's a dilation factor from the x or along the y. And so essentially we're just stretching the entire thing in the y direction. This number says 3, so it's now going to be plus and minus, sorry. The n value is a dilation factor to go. Yeah, you got a question?
Yeah, I have a bit of trouble with finding the behavior of the graph at like the endpoints of the domain after it's been horizontally translated.
Yeah, no, I know
So
you
like I'm
mentioned
not really
the...
sure like if it's supposed to go up from the point or down. Yeah, figuring that
upward.
out is a bit
Yes,
hard.
so we'll get to the horizontal translations in a bit, and I know what you mean, right? Because as soon as you get that horizontal translation bit, you're not starting at key features anymore, so it starts feeling a little bit weird.
Yeah.
We will go through a procedure that doesn't necessarily rely on that, and so having gone through this, we will build up to being able to handle that situation where you do have different domains and not necessarily super nice horizontal translations to go with it. But okay, so as I was saying here, the n term, that is the dilation factor that affects the x. And yeah, you can see that having a 2 there now, it repeats in pi rather than in 2 pi. That's using calculating the period. So the period is 2 pi divided by n. So n is that term there, the 2. And so that's why this one will repeat in pi. 2 pi divided by 2 gets you 2 pi. Okay, looks like she's dipped for somewhere else. So I think we could probably... Are you fair enough with like these ones with just the a and the n?
Yeah.
Yeah, those are cool. All right, we'll skip through that. Reflections, cool. So reflections work the same way as they always have. Fun fact for the circular function specifically, you only have a negative sign at the front rather than on the x. That's just because in a lot of circular functions, flipping horizontally doesn't necessarily do a whole lot because it can be rewritten in a different way, which is a lot easier to interpret. Here's where we get to the harder stuff. So when you get your horizontal and your vertical translations. Horizontal translations, they work the same way as they always have. Minus means shifting right, and plus means shifting left. So you can see here, this plus pi over 3, we're shifting backwards by pi over 3. When it's not a multiple of your domain, so let's imagine it was like 0 to 2 pi, for instance, because pi over 3 is not a multiple of that, you'd be looking at only this bit, right? Like this little bit would be cut off, and then this bit would continue on, which we can't quite see yet. And so that's the main thing that you're going to have to end up worrying about, at least if the domain is a mismatch. We'll have a look at how we sketch, just in general, one cycle, because that's how I will typically teach how to handle this. You start by sketching out the full cycle, and then continue to dot out all the key features, and then you basically just chop the graph off where you need to. That's the gist of it. So we'll see what that looks like in an easier example, and then we can apply that for effectively any domain. So here we go, just a basic circular function with a shift forward by pi over 2. It is a multiple of the domain anyway, of the period rather, and so it's not going to turn out too nasty, but we'll see an example where we will have to fix it up later. So here's just a bunch of key steps that you have to go through for the sketching of these circular functions. A lot of them are just like quick little one-shots. Right, so find the period, 2 pi divided by n. N is going to be from here, n is 1, period is 2 pi. Peak and trough are going to come from here, plus minus 3, nice and easy. Here's where you start to have to handle the horizontal translation bit. So first up, figure out your period and divide it up into 5 equal parts. So the way I'll always typically do this is you go 2 pi, which whatever the number is for your period, you start with that, halve it again, and then just backfill. Now from here, whatever your horizontal translation term is, adjust the numbers that you just created from there. So you'll lightly pen these ones, or lightly pencil these ones in, and then in your head imagine, okay, I'm shifting everything forward by whatever the translation is. Now in this case, pi over 2 was a multiple of the period, or rather a factor of the period, so they did end up sort of lining up nicely. But if you had pi over 3, for instance, this one would shift forward to pi over 3, this one would shift forward to whatever that ends up being, and so on and so forth. But you're still going to have an array of 5 values. They're just not going to have the same they're not going to be nice and easy multiples of it. From there, depending on if you have sine or cos, you'll dot it out accordingly. So in this case, we have sine, so regular sine starts at the middle and goes to a peak, and so you just continue to dot out that, that overall shape. From here, we can work on finding x and y intercepts. When there's no vertical translation, your x-intercepts are already solved. Right? They just are those dots that you've outlined. You should also check your domain and see, do you even bother finding a y-intercept? Because in this case, our domain was from pi over 2 to 5 pi over 2. So we don't even have to bother. But if you did need to, you would just sub in x equals 0, like you would for any other graph. And then, yeah, all we do is draw the curve connecting that. Here's how you now adapt it for a new domain. Let's say you had to do from 0 to 2 pi. Basically, or even let's even go a step further. And let's say you had to do, what would this end up being? Let's say we had to do there, right? Or even, yeah, excluding that 0, right? Like we're ending at non-key features. What are we doing there? Well, all you're doing is whatever these endpoints end up being, you sub those in, and then you just simplify the circular function. So what would it be? 3 pi over 4, 6 pi over 4. Let's say this one's 7 pi over 4, right? This n bit here. You just sub in 7 pi over 4 into your circular function, get whatever the value is, and then you cut it off here. Same thing over here. If that's like pi over 4, for instance, you sub in pi over 4. Whatever the value is, it's going to be somewhere down here. You label it, and then that's how you end up handling mismatched domains. you always start by drawing one cycle and carving it up into these 5 equal parts. Because when you do that, you can continue going backwards and forwards as many times as you need to fit out the rest of it. Like, let's say the domain ended all the way in the negative side somewhere. Well, if we know that pi over 2 is all of our separators, then we just continue going backwards by pi over 2, dotting it repeatedly over and over again backwards until we go further than the domain, and then we just chop it off before we get there. Is it fair enough, the idea of what you would be doing there?
Yeah. I have one more question. So if there's a horizontal translation, then the domain is the same size as the period. Will the starting and ending y values be the same?
Most of the time, yeah. That's what I've found to be the case a lot of the time. I can't say all of the time. So what are you saying, like, if this was 0 to 2 pi, because 2 pi is a domain?
Yep.
Yeah. If this was 0 to 2 pi, then yeah, you would see that, because the next thing going backwards would be a trough at -2, and then at 2 pi you also see -3, I should say. Trough at -3 here. A lot of the time it does end up being the case, and because, yeah, if domain is going to be a factor of the period or vice versa, then yeah, you should be starting and ending at the same point no matter what.
Okay. Thanks.
Sweet. Vertical translations make this a little more complicated. So they can either be really nice to you or they can be really bad to you. If you have a big vertical translation, it won't touch the x-axis anymore. And that'll be nice because that means you don't have to give any of the x-axis features anymore. No x-intercepts required. You do still have to dot out where the key feature is going to be to separate it up. So you'd have your 2 pi for the full domain, or for the full period rather, and then carve that up into the key features dots, but you don't then have to like label the x-intercepts. It's more about you getting the graph proportionally correct. Whereas if you have a less than pleasant vertical translation, you will still be doing the 2 pi over 2, carving that up into the equal parts, but you'll also see that your x-intercepts are no longer on those key features anymore. And so for that reason, things get a bit harder. So we just adjust things ever so slightly by adding this additional step into our procedure, finding the x-intercepts, which for any function is just letting y equal to 0. So here's an example. We got a vertical translation of 1, but an amplitude of 2. So because of that amplitude of 2, we are going to end up carving through the x-axis in less than pleasant spots. Again, n is 1, so the period is going to be 2 pi. Peak and trough, just keep in mind, it's not always necessarily just plus minus 2. Because you're shifting the whole graph up by 1, you now have to account for that with the peak and trough. So you have plus minus 2, and then you're adding 1 to both of those possibilities there, which gives you a peak of 3 and a trough of -1. Once again, divide it up into the 5 equal coordinates. For 2 pi, that's probably pretty easy. Halve it to pi over 2. If it's anything else, again, you're still just doing half and then backfilling in the remaining thing. The numbers could get different, but it's fundamentally the same idea. Doesn't matter what the domain is, always start with getting just that initial scaling correct, making sure you have the separation as necessary. If you have a horizontal translation, make sure you apply that to this as well. So just adjusting the numbers to, adding or subtracting the horizontal translation depending on what you had. In this case, we had none of them. From here, dot it out. So we knew we had trough at -1 and we had peak at 3. In this case, it was a negative cosine. Cosine normally starts at a peak. Negative cosine, therefore, would start at a trough. From there, it has to go to the middle, then peak, then middle, then trough. You draw your curve and you realize, oh shit, I've got these things to worry about now. So, just like any other x-intercept, you solve it by setting the y equal to 0. So that was the function. Y equals that. Now y equals 0. rearrange, and then we use the procedure we were talking about last time, last lesson, which was how to solve a circular function. So essentially you rearrange to get the circular function on its own and one of the exact values on the other side. Then you look at your unit circle to figure out where are all the solutions to cosine equals a half. What that means is you would pull up your unit circle in your brain, because you're not allowed to have a printout in the actual thing. And because it's cosine, you're looking for x values. And because it says cosine equals a half, you're looking for all the spots where x is equal to a half, or where the x coordinate is equal to a half. Hence, you're going to have the pi over 3 and the 5 pi over 3 options there. And those become the x-intercepts. You label them accordingly. And just do a quick sanity check. Make sure those values do in fact make sense to fit there, depending on the scaling of the x-axis. You know, if you had like 2 pi over 3 here, for instance, some alarm bells should be ringing because one of your things have gone wrong there, whether it's you've done the solution poorly or you've done the scaling poorly. And again, yeah, as long as you follow getting your initial, like spreading it out in 5 equal parts, you just continue to add or remove parts according to whatever your domain is. And if it doesn't end on a key feature, you just sub in the endpoint, the x value of that. So let's say it ends a little bit further, you just sub in whatever that value is into the function, solve it, and then, yeah, label it with whatever the value is. Anything to clarify further about any of that? We kind of ran through all of that.
I think that's about it.
That's fine? Cool. Let's do some practice. Okay. Functions, where is that? Sine and all the way in 14, probably H, but maybe I. A. Is I going to have anything crazy in there? It is. Okay. Let's do it with both then. Cool. Oh yeah, I should probably get my... I'll drop the unit circle in as well as the notes for sketching sine and cosine for anyone who wants to use that procedure to follow along. And I think for this one we'll do 2e, because that's going to have both the horizontal and the vertical translations in there. We'll see how we go. Okay, so that's going to be y equals... Oh yeah, by the way, the way they write these is a bit tragic. So you got 2 cos, and for whatever reason they like to put the n term out of the bracket here. I don't know why they do that, because technically speaking it should be included there. Just know that's not like cos squared, for instance. It does in fact mean there was a dilate factor of 2 in there. Cool. All right, that's the graph, and the domain for this one, which we should be able to practice the mismatch on this there, because we have negative pi to 2 pi. Just worth pointing out, in an exam or SAC, you've never had to sketch more than 1 cycle worth of the circular function. I'm saying that because I'm noticing this domain is many times more than the period. The period of this one, well, we'll find out once we go through it, but this is several cycles, whereas when you're actually in the real exam or SAC, you only ever have to do 1 cycle. That won't necessarily mean the domain will be nice and easy for it. You might still have to do the same sort of subbing in endpoints, but just to point out, this is going to go excessive for the amount of things we'll be sketching. But with that out of the way, let's give it a shot anyway. So, how can we start? We need to get some key features. What can we determine?
We can determine the amplitude and the period.
Yep. What's that going to end up being?
The amplitude is 2 and the period is pi.
And yeah, the period is pi because period is always calculated by 2 pi divided by n, where n is 2 in this case. So period is pi. And the amplitude being 2, that also came from there. Nice. Okay, got amplitude, we got period. What else?
Okay, so the vertical translation is down 1.
Down 1.
And
Yep.
the horizontal translation is pi by 3, right?
Yep, that's all good. Okay, so as far as representing that on an axis, how do you start representing that on the axis?
So do I represent the minimum and maximum, or?
Yeah, I mean, you mentioned the translations. I just wanted to see
Yeah.
like where you would what you would start doing with that. And yeah, I would be starting to label like peaks, troughs in the middle, that sort of thing.
Okay, so the maximum would be 1 and the minimum would be -3.
Yeah, because you got plus minus 2, but everything's been shifted down by 1. I would also go ahead and probably put the middle in there as well, just so you know where to put the middle dot when it comes up. You also mentioned horizontal translation. That gets you something.
Yeah. So horizontal. How do I represent the horizontal translation?
Yeah, so there's a couple of ways you can do it. The way that I've written explicitly in the notes is for like absolute beginners to it, which is I say, don't worry about it for now and just focus on the scaling first and then apply it later. What you'll see quickly is that that requires a lot of rewriting. So I'll do both ways. One which is the slower but more methodical, right? You get further quicker with the next way. But first we'll just keep it basic. So the initial scaling, right? We have a period of 0 to pi, which, well, we have a period of pi. So if we just assume bare bones basics 0 to pi, we would set up our equal parts. 4, 3 pi over 4, and 0 counts as one of those. Then, once you've got that sorted, everything needs to be shifted forward by pi over 3, essentially. So this one will end up like there, that one will end up there, so on and so forth. So you can see how that might be a little bit of rewriting. But at least it gets you something visual to start looking at. So, like maybe off to the corner, you might do something like 0 plus pi over 3 is pi over 3. That's, a really obvious one. Then you'd have the pi over 4 plus pi over 3. That's a bit of a harder one because now you've got to start working with different denominators. So doing a quick cross multiply, you'll have 3 pi and you'll have 4 pi, sorry, plus 4 pi over 12. I definitely did that right backwards, yeah? Yep, that's it. 4, 5, 6, 7 pi over 12. So, you can even label them as you go. That's 0.1, that's 0.2. And the good news is, doing this conversion, oh sorry, I've just seen a question come through. Just fix my screen, you haven't been able to hear anything. Would you be able to go through one more example? Yeah. I think what I'll do is I'll try just quickly re-explain this one and catch you up. And if that's still not quite enough, we'll do another example end to end. Fair enough? Okay, so more or less just following the procedure that we were outlining before. First things first was to get some basics, right? So we had the amplitude, which came from this term, and we had the period, which is calculated by 2 pi divided by that term there. Both of the dilation factors, basically. These are both outlined in the steps. In fact, I'll even have those up on the screen share. Step 1, find the period. Step 2, finding our peaks and troughs. This vertical translation -1 meant that instead of having plus minus 2 on our peak and trough, it's now shifted down by 1. So that's why we have this 1 and this -3 there, and our new midline at -1 instead. From there, we were now discussing how to handle the horizontal translation. The way I'm proposing you start with is to start by looking at the period and then break it up into 5 equal parts. So that's what step 3 says. Divide the period into 5 equal x coordinates. So you start at the period value, pi, and the easy way to do it is to halve and then halve again. So pi becomes pi over 2, becomes pi over 4, and then you just, you know this is now pi over 4 separated, so you just count back until you solve this one. That gets you an initial scaling. As for where we're currently at, we're now applying this horizontal translation to it. So this pi over 3 shifted right, we look at each and every one of these 5 points and add pi over 3 to it, essentially. And that's what's happening here. 0 plus pi over 3, pi over 3. Pi over 4 plus pi over 3. We do a bit of fraction arithmetic, and we get to 7 pi over 12. That catches us up from where we left off. What I was then saying was, once you've already done this conversion of how pi over 4 and pi over 3 works, you can now just use that for the rest of them. So for instance, the next one up to shift is the pi over 2. Instead of adding pi over 3 to it, you can add 4 pi over 12 to it. You've already done that math. You don't have to do it again. And converting these into that denominator is a lot easier. So pi over 2 becomes 6 pi over 12, 10 pi over 12. Yeah. You'll even start to see how to count it from there as well. So you can see these are separated by, what is it, 7, 8, 9, hang on, did I count that wrong? 5, 6, 7. Why does that feel off? We should be adding 4 every time. Maybe I'm just losing it. Anyway, 3 pi over 4 plus 4 pi over 12, and so on and so forth. So 3 pi over 4, 4 3s are 12, so that's 9 pi over 12. 10, 11, 12, 13. Yeah, I guess we are adding 3 pi to it every time. Thought that was a bit weird, but I guess. So we got 7, 10, 13. The next one we should imagine as 16 pi over 12, which will simplify. 16 pi over 12, 8 pi over 6, 4 pi over 3. Then we're just going to relabel everything in here with those values. So we don't have the origin tick anymore, but we do have a new tick that's going to be a bit further up. Okay, got our pi over 3. We got our 7 pi over 12. Got our 10 pi over 12, 10, 13, and 4 pi over 3. And now that gets us our full cycle in the spot that we actually wanted it to be based on the horizontal translation. You can see it's a lot of messing around, right? There's a lot of effort that goes into these, which is why you'll often see that sketching circular functions is worth up to like 3 marks in a SAC or an exam. There's a lot of messing around with it. So we got our X information sorted, we got our Y information sorted. I'm just going to get rid of this stuff because it's getting in the way of the sketch. all we're going to do is start dotting things out. So cosine, right? Cosine starts where, in this case, if we think about this as our starting point, what y value is our starting point going to have because of its cosine? Anyone remember the basic version of cos? Where does cos normally start?
Is it going to start from the top?
Yeah. So cos always start at a peak?
Yeah.
Yeah, that's right. And so yeah, since our peak is 1, we started at 1. Then it's got to go to a middle because there's nowhere else for it to go. And we just continue to dot everything out. And that gets us one cycle. How do we now fill in this stupid domain? We just keep drawing these ticks. So all this math that we're doing here by repeatedly adding, effectively adding 3 pi over 12 every single time, that's what we're doing now. I'm going to keep doing that until we hit 2 pi in that direction, and we're going to keep subtracting 3 pi over 12 until we get to negative pi. You can see this is excessive. Okay, cool. So 13 pi, that'd be 16, 19, 21, 22, 24, 25, 6, 27, 28. Maybe at this point I'll check, because these should all be over 12. 28 pi over 12. Too big there. It's going to be 14 pi over 6. 8 pi over 3. 8 pi over 3. Not too far. Looks like it. Because 2 pi being our maximum would be 6 pi over 3. So we don't want to go that far. How about 25 pi over 12? I was told to 24. That's a little bit above again. So you can see it's more than 2 multiples of 12. So again, we're going to ignore both of those points and cut it off ever so slightly beforehand. So we know this is not going to be one of the key features. So when we continue to dot it out, we go middle, trough. This is not a middle anymore. It's pretty damn close to a middle, but it's not actually going to hit a middle there. So we just got to sub in 2 pi and validate what that is. Does anyone want to see the tech-free version of me subbing in 2 pi and solving the value? Or do we want to just sort of cheat it out, given how big it is? Yeah, we can, sure. Okay. Y equals, okay, 2 cos 2 bracket. So x is now going to be the 2 pi. And it is minus pi over 3. Minus 1. Okay. So first up, just simplify the inside of the bracket there. 2 cos. So we're going to have 2 bracket 2 pi minus pi over 3. So that's going to be 6 pi over 3 minus, so 5 pi over 3. And then doubling that to 10 pi over 3. Now, because we know the angle inside the circular function, we can solve that one ourselves from there and get the actual value that ends up equaling. This will be a bit of revision from what we did last lesson. So this angle does not appear on the unit circle. Does anyone remember what we do to make it easier to evaluate this sort of thing?
Do we convert it to equivalent fraction that we can find on the unit circle?
Equivalent, yeah, it depends on how you mean though. So how are you going to do that?
Wait, so it's already over 3, so
Yep.
we can just it's going to be the same as 3 pi over 3, right?
Is it going to be the same as pi over 3? I'd have to look at it to make sure, but it is a pi over 3 type angle. Just for those who have recently joined, by the way, we're looking at the circular function stuff. Specifically, we're looking at the sketching side of things, but where we are at right now is evaluating a circular function. So all these things sort of play together. This is a review class, by the way, so I know this is normally a Unit 1 and 2 thing. This is probably a bit early for Unit 1 and 2 people, so just keep in mind this is specifically a review class. But okay, so how do we now go about doing that? A couple of ways. I'll bring up, yeah.
Can we, if the angle is in the third period, right? Because 10 divided by 3.
It might be. Again, it's not, if we look at the unit circle, so if I pull up on the screen share, like, top right corner screen share bit, 10 pi over 3, like we cut out at 5 pi over 3 here. That's as far as this goes. So we have to figure out where exactly this is going to end up. And one of the things I suggest for larger angles is to break it up into an integer value of pi and a fractional value of pi. So I think this is what you were sort of talking about, which is getting a mixed fraction, basically. So you see how many times does 6 fit into 55 in the example that I've got on the screen share, and that's going to be 9 with one remainder. Then from there, it's a lot easier to work with because any odd pi will start on the left, any even pi will start on the right. And so, yeah, you can now just go to the next pi over 6 that's from the left-hand side. So in this case, 10 pi over 3, we first figure out how many times does 3 fit into 10. It's going to be 3 times with one remainder. Because we now have an odd pi, means we're starting on the left, and we're going to the next pi over 3, which, if we look back at the unit circle, would be the 4 pi over 3 spot. So 10 pi over 3 is the same value that would be located at 4 pi over 3. It's complicated, I know, but hopefully seeing the idea there makes it a bit easier to comprehend. This is probably the best way of going about that, because when you have a big nasty fraction there, you could technically count around, because that's effectively what we're doing here. We're trying to circumvent counting around a bunch of times. If you look back at the screen share, for instance, like this 7 pi over 3 thing, the unit circle is broken up into pi over 3 type angles, but because you can only go up to 2 pi, it's got to stop. Well, you can keep actually counting around over and over again. So you can actually see there's our 10 pi over 3 in that 4 pi over 3 spot. But okay, so now that we know we're at the 4 pi over 3 spot, we now need to figure out which of these values is valid. We have cosine, so which of those values is going to be valid for our evaluation? Yeah, mate, go for it. You got your hand up, Christopher? If you're talking, you're muted. Maybe message me if your audio is bugged. Anyway, Nihal, maybe want to give it a go?
Yeah, so you're going to take the x value?
Yeah, the x value, so -1/2, right? These are coordinates, so that's an x, that's a y, cos is always x. So -1/2 is going to go in that cosine spot, right? Cosine 10 pi over 3. We did some legwork. We now know where it is on the unit circle. We replace it with the -1/2. This -1 is still going to be here, and well, this is just pretty simple, right? 2 times -1/2 gets you -1, -1, -1, -2. And so that should make amount of sense because we know we weren't stopping at the mid-level, which is -1. So the middle would have been here at -1. So in reality, it looks like this dot should actually probably be a bit further backwards. Oh, sorry. This dot, because that's the midline. If you want, you can actually sort of dot out the midline kind of like that. So proportionally speaking, we should probably end up like there-ish for 2 pi. I think we should... Sorry guys, your audio just maxing. Sure. Yeah, hopefully the audio sorts itself out soon enough. Let me know. Maybe even just like a sort of rejoining could potentially help. Not too sure. I think we could probably just leave this example here. We've gone through and seen how we can do multiple cycles. We've gone through and seen how we can fix up this domain when it's not a nice even thing. We would just be doing the exact same thing going backwards here up until negative pi. Do you guys want to see me do that? Or have we got the gist of what's going on there?
Okay, so the circular function translations make it quite complex. So how
Yes.
long are we expected to spend on one question?
Yep. So I mentioned these are typically 3-mark questions, and considering it is 1.5 marks per minute, well, that'll give you your answer. So you get a lot of time to do these. And so if you can get good at these, honestly enough, a lot of the stuff I was going through here, as I sort of said in the beginning, you only ever have to do 1 cycle. So in an actual SAC or exam, and that's still with the 3 marks, by the way. So this would have been cut off several dot points ago, right? Like maybe from here to here, for instance. And so we've done a lot more, and the whole time I was explaining things as well. So in reality, this isn't as long as it looks. All of these things should be free immediately, right? Finding out where your peak, troughs, and period is, that should be nothing. Like that should be done in like a fraction of a second. How do you calc the range? Yeah, the range, that was based on the value here and the value here. So this bit here tells you your plus minus, like your peak and your trough. And because this bit at the back is a vertical translation, you essentially take that initial plus minus and shift it according to what the vertical translation is here. So we start with plus minus 2, because this number says 2 here, and then we shift each of those down by 1 for that. So that'll get you your range of your peak and your trough down there. We start at the 2 and the negative 2, and then you can see both of those are shifted down by 1 because of the vertical translation there. Does that answer that? Sweet, no worries. Cool, all right, so yeah, as I was saying, as you get good at these, that sort of stuff will become immediate, right? Like all we did was an addition and a subtraction there, right? Like that's nothing. Period, 2 pi over n, you're just taking it off of that, that's immediate. Where things get a bit harder is with the translation stuff. Vertical translation, not so much, that just only plays at the y stuff. Oh geez, we didn't even do the x-intercepts. Oh god, yeah. Because, you know, when you draw this, you now have to also get these as well. But we won't worry about that just for now. Yeah, Taihan?
Yeah, what's the actual like mark allocation for the graphs?
Mark
Like
allocation
if it
for the
was
graphs,
3,
yeah.
like what is each mark? What are you getting each mark for?
Yeah, that's a good question. I haven't actually really considered what it's being allocated to. I would also honestly be more considering just it being allocated based on time more than anything else.
Okay.
What
So
could it
would
be
you say it's
allocated to?
more like globally marked, as in like this, so we'll just kind of look at your graph as a whole?
Yeah, what do you... So the last mark is always going to be if we're getting the full thing right. How would I start marking things? Let's say if you can get your... What do you need to have happen? Let's actually... We can look at all the steps. It's good that I've written down all the steps you have to follow. Yeah, even if you just sort of break these into thirds, right? So maybe finding your basic features of period, peak, trough. That might be 1 mark. getting your scaling correct, so dividing it up into 5 and shifting it accordingly might be one. And then tidying things up at the very... Yeah, same question. Or, yeah, everyone has the same questions, don't worry. And then, yeah, going from there, just sort of tidying things up with all the Y stuff and subbing in endpoints. That'd probably be the gist of where it gets separated.
Yep.
Do we actually have a... There might be an actual marking scheme. I just have to find one of the tech-free exams that actually...
Would that be something that would be on the the final exam assessor's report?
Yeah, that's what I was going to look for, because I assume, because, they got the number of marks are awarded for different things that come up in the questions, so I'm going to take a peek. The problem is I just got to find it, so we might be sitting here for a little bit before I find the one that had a circular function graph in it. But I think it's worth looking at. We don't have too much time to go through much else, so let's have a look and be certain where the marking is going.
Yeah, I just wanted to know because I assume there's different features that you kind of need to hit. Like, obviously, if you want full marks, you've got to get the whole thing, but...
Yeah, look at this. This is not even a sketch, and this is 3 marks. Like, they're giving you 3 marks just for finding x-intercepts here. And they've already given you the graph to look at. So that should already tell you a bit about, how well marked these, when you have to do the sketch entirely. But let's see if we can find one from start to... Actually, no, I know it was... What am I saying? I did this in my exam. It's got to be the 2018 one. And I stuffed it up in the exam too. Yeah, here you go. Yeah, 2018, mate. I graduated 2018. It's been a while. So yeah, the one that they got you to sketch, got me to sketch anyway, was a very basic cosine, no horizontal translation involved, just a vertical shift up. I don't know how I screwed this up, man. I think I screwed up the period here. I made it, I tried to draw 2 cycles in this because I saw 2 pi. I was like, oh, 2 pi means 2 cycles. No. They got the scaling laid out for you, so that's another thing to help out. Let's see where the marking scheme went. So this was part B of question 3. Question was well answered, so most people got the 3 marks. Some students did not label the 3 key points. Students took care of the shape. Okay, there's not too much information there, unfortunately.
So I feel like it's a bit more holistically marked in, and then just if they see a feature that you haven't included, then they'll just maybe cut a mark.
Yeah.
I think that's the kind of vibe I get.
Yeah. Surely almost always. Yeah. I feel like these you pretty much would always full mark unless it's somewhat likely you might stuff something up a little bit, but if you do stuff something up, you'd feel like it'd stuff up everything, right? Like, you can't really screw up the scaling. It's given there to you. There's no horizontal. There was nothing to sub in to solve for a value. So they're treating you nicely with what shows up in tech-free. And tech-active, you don't have to care about any of this because you just graph it on the CAS and then just use the CAS stuff to sort it out. So, we're going through these because the book goes through these. And because the book goes through these, it means that your SAC might do it. So this isn't really an exam thing to worry about too much. As you see, the exam one is actually quite chill. There's just a vertical translation, and everything is nice and neat within the domain. But because it's in the book, your teacher may or may not be quite so pleasant, because in the book they do all this shit, which is ridiculous. This is well and truly beyond the scope of what you should need. And we didn't even finish this question, right? To put it into perspective, we had to go all the way back to negative pi, and we didn't even do the x-intercepts. Maybe we'll wrap this one up with finding the x-intercepts of this, just so we can know how to solve the x-intercepts. And that should probably take us to time. For methods, the exam is the main. Yeah, so the exam, has a nominated percentage that it goes towards your study score, with the caveat that it also scales your SAC results as well. So, for instance, if you do really, really well on the SACs but bomb the exam, let's say hypothetically the SACs are 40% and the exam is 60%. I don't actually know what the proportion is. It doesn't just mean you get 40% as like a net grade. You might get 30% or something like that, because the exam stuff actually scales the SAC results. So it's both good and bad news. It's good news if you're falling behind, because it means you have an opportunity to get back up, because if you did bad in your SACs but really well in the exams, your SAC scores actually get scaled up. The reason why they do it that way is because the schools are independently moderated, and essentially what's happening there is VCAR, the assessors, are going to say, okay, you did really bad on the SACs but really good on the exam. Either your SACs were too hard, and so we should, reflect that by giving you better grades, or for whatever reason you've pulled your head in and you've locked in, and for that reason you should be rewarded for getting it right at the end. Heard schools like Melbourne High have Melbourne High have insane SACs. I've heard it a couple of times on the calls. In fact, we get a few students from Melbourne High that come in for this specifically because they're like, hey, look, the SACs are awful. What can we do to handle this? Which is why, we look at these harder questions, because although the exam will be, there you go. Because although the exam won't have this level of complexity, your SAC might. And even if it doesn't, it's good to understand these fundamentals quite well. Anyway, that was a big rant from me. If there's anything to clarify there, I know I talked a lot. Let me know if there was anything that wasn't super clear. I will continue on with getting the x-intercepts for this, unless someone has a different question. So where we left off, we had dotted everything out. We had finished off the endpoint and got the required value. So should have been y equals -2. So essentially this would have been labeled 2 pi comma -2, that one there. But because we had a vertical translation, what we notice is that these x-intercepts are not part of our scaling, right? And so for that reason, we now need to start solving them individually, which is done by just setting y equals 0, right? For any x-intercepts, you always do y equals 0. So 0 equals 2 cos bracket 2 bracket x minus pi over 3 minus 1. This goes back to what we covered last lesson, where we don't know the angle, the x thing in there, the thing in the brackets is what we don't know. But we do have other information, like what value it should equal. So who wants to take a stab at following up with this one? How do we start working towards getting a solution for x?
We can take the -1 to the other side and then 2 to the other side.
Yep, that's it. Half equals cos 2 bracket x minus pi over 3. I can already see this one's going to be nasty, but we'll get there. That is the good start. Getting the circular function on one side and one of the exact values on the other. We'll recognize a half from the unit circle. What do we do from here?
We can find the values for like x. You can find the value of cos of x equals to 1/2.
Yeah, that's right. So we're looking for all spots where cos, so the x coordinate, should be equal to a half. And lucky enough, we actually did one of those examples already. We already know it's at pi over 3 and 5 pi over 3. Now, the weird thing here is, because there's not just x in here, we don't go ahead and just say x equals pi over 3, comma 5 pi over 3. We don't quite do that. What we say is all of this equals pi over 3 and 5 pi over 3. Because that's what ends up actually being the case. It's this stuff which is why if you have a basic cos, since it has a just x in there, we do just go straight to the solution. But because there's more stuff involved, we now need to have 2 bracket x minus pi over 3 is equal to all those things. Furthermore, we don't just do one cycle, right? We can now refer back to our graph to figure out, okay, well, one cycle would have got us that and that solution, but if we look at our graph, we know we need to get the next one as well from over here. Which is why having the graph drawn already is kind of nice, because it can be a bit deceptive how many solutions you need. Because when you look at your domain that extends out to 2 pi, but you start at pi over 3, it can be a bit sort of weird to figure out how many solutions. Looking at your graph, I cut there, there, and there. I need one more. So instead of just having pi over 3 and 5 pi over 3, you got 6, 7 pi over 3. 7 pi over 3 would be the next version of that pi over 3 spot in the first quadrant. Are we clear enough on how all of those were gathered? If so, let me know where we go from there.
We can take the 2 to the other side and divide it with all 3 of them.
That's it, yeah. We're just going to start unwrapping for x. Divide everything by 2, so now that whole thing goes over 6, essentially. And then, yeah, you might even just want to rewrite this as 2 pi over 6, so your addition becomes easier afterwards. That's it. Okay, so pi over 6 plus 2 pi over 6, so 3 pi over 6. I know that simplifies, but probably better off just do it at the end so you can get into the flow of things. 5, 6, 7 pi over 6, 7, 8, 9 pi over 6. X equals pi over 2, comma 7 pi over 6, comma, what am I doing? Don't know why it took me that long to brain fart on that one. But okay, so we should expect this to be pi over 2, which, you know, 7 pi over 12 is a bit more than pi over 2. Pi over 3 is a bit less. So sanity check, making sure we're getting things in the right spots. 7 pi over 6, 3 pi over 2. Oops. 7 pi over 6, 3 pi over 2. Yes, I know that's a massive mess. I guess worth considering, how do you make this tidy for your actual axis? What you can do, and I've started to kind of do it here, is I'll keep the scaling values on one side of the axis and the x-intercepts on the other. So for instance, all the scaling's on the bottom side of the x-axis, but any x-intercepts I'll write on the top part. You might not want to draw these arrows. I'm kind of just, you know, doing my best to keep it all in the same thing. But in your SAC, you're going to have an actual axis that's spread out nice enough to make that work. Yes, Taihan?
We've been told that you can get marked down for like feathering your graph. Like if you if your graph isn't like one continuous line. Like does that happen in the final exam as well?
One continuous line. I don't really know.
No, as in like when you're drawing, like for example, when you're drawing, like you might just stop at a point and then go again, or like go over the same line just to make sure that like you know it's correct. Yeah.
I've heard something about saying like don't shade it in like that. You know, like doing this whole blah 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 blah, that sort of thing. Yeah, avoid it. I think I remember vaguely something like that being mentioned to me as a tip for the final exam, so it seems like that's propagated all the way down to yourself as well. So probably keep.
So would it be good to do kind of like when you're like first making a graph, maybe like a lighter line, which you can like easily erase and then to like do it properly?
Yeah, I mean, So having the dots is going to be the main thing because that'll let you actually draw this line properly. And then, yeah, if you want to sort of from there lightly draw it and then draw over it because you get the grooves into the page, that's one thing you can try and do.
Yeah.
But,
like, would you get marked down, like, sorry, I know I'm being really specific, but
no, that's fine.
Could you get marked down, like, say, if your line doesn't, like, perfectly intersect the dot or something like that?
No. I mean, look, if you're doing, like, what I've drawn here, I reckon is, even if it doesn't look it, like, acceptable. So you can see, like, this isn't exactly on the, where is it? This isn't exactly on the dot. Granted, if you had a look back at the, I'll pull it up again. We had the exam that we were looking at, the 2018 one. There's a grid. So it also helps a lot there because you can just use the grid lines to help out. As you can see, it's directly on there. It's pretty hard to screw up when there's a grid as well.
Oh wow, they give you a scale as well.
Yeah, this one had a scale. That's the exam anyway. The SAC, every SAC I've seen in my private lessons that's had this, I believe has also had a grid. So should be fine. And if not, again, this sort of stuff that we're talking about here with being able to dot it out, scale it, it's all still applicable. Cool.
Yeah.
Okay, cool. We made it time on that one. We will be going over this again tomorrow because that's when it was actually scheduled for. We're doing this ahead of time because it's a review class. It was meant for anyone who wanted to go for anything specific. We'd do that. If you don't mind asking, I was wondering how you went for methods yourself, maybe tutor, and what I'm currently... Yeah, that's fine. I'll answer that in a moment. I'll just conclude the class. So yeah, class is effectively over now. We've hit time. If there's anything you want me to clarify further, feel free to stick around for a bit, and I will see you in the next one. As for how I went in methods, I got a 39 scaled when I did mine. So even though I did screw up this this graph here, it didn't turn out too poorly. And so yeah, 39 scaled on that. What that typically looks like is you're scoring 80% plus on most of your SACs. You're getting all the homework done with relatively no effort, and essentially by the time I had done the actual exam, I had done, I forget the actual number, but it was anywhere from like 6 to 8 practice exams. So literally looking at the past exams on the VCAR website and doing, I think it was probably 6, because there's a tech free and a tech active, right? So one exam counts as 2, right? 3 hours worth, because your exam 1 is 1 hour, your exam 2 is 2 hours. And so, yeah, I had done 6 pairs of exams before then to reach that level. So if you're looking for something similar, that's the level of effort you'll be trying to benchmark yourself against, I suppose. What made me tutor? I was bored at my job. I had moved to Adelaide for an engineering role. So I did methods and all that stuff to get into to engineering, and it was fun, you know, but because I was in Adelaide, there wasn't a whole lot else to do after that. And so I just kind of did this for fun for a bit. And then it turned into its own thing. How realistic is a raw 38 if I was bang average or slightly below average? I mean, you're starting now. You're starting to improve things now. I mean, you'd be less advantaged than I was because I had never really had trouble with methods. Oh, 35 plus. Raw 35, I mean, that would be more or less what I got because method scale is quite high. If not, maybe a bit. Maybe I got like a raw 36 or something. I don't know exactly how it scales, but it scales higher. Yeah, you might be slightly less advantaged than I was with it if you were bang average, because again, I was averaging 80s and maybe like dipped to 75 at worst. There was one SAC I actually fully bombed, one test, but that was a different story. Everything else was well and truly at the 80 plus. So if you can get back to that stage quickly enough, yeah, getting a raw 35 should be pretty chill, because that'll scale you up to probably 39-ish. That's just me sort of saying numbers, though. I only really know I don't remember my raw too much, just what it's scaled to. And now we're at time. You have a few minutes to go over one more example since I missed the start. Yeah, why not? We can do another example. Not nearly to the extent of that complexity though. In fact, we could probably just do this this exam one if you wanted to. Let's do that. Okay, so if anyone wants to see another example, I'll do that, and we can do that. No, good. It's fine. We take additional. There's additional time built into this to clarify any lingering concerns. So that's fine. So the graph we're going to be sketching is from an actual exam, so that's pretty cool. 2 cos x plus 1, and we're doing it from 0 to 2 pi. So one of the simplest kinds of things you can come across. We're given an axis as well, so let's go ahead and just get that scaling sorted as is. So let's go 2 pi, pi over 2, 3 pi over 2. I guess they do have the other. I kind of just went off rip and did that myself. I didn't expect them to have a different scaling. Let me grab that then. So what they actually had was 2 pi. How many ticks are there? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Pi, 5 pi over 3, 4 pi over 3, pi, 2 pi over 3, pi over 3, and the 0. Cool. As for getting our peaks and troughs, that's going to come from these terms here. So it's going to start at plus minus 2 and then shift up by 1. So instead of being 2 and negative 2, it's now going to be 3 and negative 1. Like that. And because that's plus 1, instead of our middle being 0, like it normally would be, our middle is now at plus 1. Then from there, they had their scale already written. I would lightly pencil over the top of it and then rub it out later to get the key features of like the peak, trough, and middle. So 2 pi, pi over 2 is going to be somewhere in there. Pi over 2 is going to be something like that. And 3 pi over 2, something like that. Then from there, it's cos, so it starts at a peak. And because it starts at a peak, the next thing has to be a middle. So it'll middle around there-ish. It'll trough at the pi mark. It'll middle around there. It'll peak around there. At that stage, we cut out those because we're using the scale that's already given to us. Oops. And then we draw. So we're going to note that there was a bit of a weird scale there. So what we're going to do is assume that that was there for our x-intercepts. So when I'm drawing that, I'm going to cut through those. Now, in this actual exam, we already solved this ahead of time. In part A, if you have a look back at the screen share, they got you to solve for x-intercepts. And I would take a very good guess at saying that those are absolutely the what I had there, the 2 pi over 3, the 5 pi over 3. Let's find out. Oh no, it is 4 pi over 3. I just read the thing wrong. Yeah. So it's exactly what we expected there. So I guess in reality, this is a 5-mark sketch. You get 2 marks for solving your x-intercepts in a separate spot, and then you get 3 marks for drawing the whole thing. You get so much time for doing this. And I mean, I finished, didn't I? Like that's it. in the time it took me to say that and explain it, that's, well, 3 marks. We would have had to put in some work to solve the part A bit, but that's not going to take much. If you have a look at the, it's what we did before. Get the causal intertone and then look at where it is on the unit circle. So that's a lot of marks very quickly. So even though it looked like we were doing a lot there, that's only because I was trying to get you to handle the worst case scenario and build the fundamentals of these things. Cool. Anything to clarify further there? Tech free looks like a bit more free. Yes. Yes. The practice stuff, the score related stuff is often significantly different to what you see in the actual exam. Especially now that they started introducing these what do they call them? The investigation SACs. Those I didn't have those when I was in when I was doing my school, so it's a bit different. Yeah, Taha?
Yeah, do you have any advice for the investigation SACs? Because, like, I've heard they're pretty hard.
Yeah, the best I can do is, if you have a look at the school website, you'll see there's a spot in there, practice SACs. There's a folder at the top, maybe it's the bottom, I don't know, it's one folder for investigations. And what that is me looking at all the investigation that I had ever seen in my private classes, and I put them in there. The investigation could range from so many different things that I don't feel like I can run a class that says, this is how you do investigations, because they're just different. And so the best I could do, in my opinion, is show you what all of them have looked like, and maybe your school will be somewhere in the middle of those. So it's more like an exposure thing. Get exposed to as much of those that are in there as possible. There's going to be some through lines. Like a lot of the time, it's going to break down to effectively when you would use sliders on a CAS for the graph. When you kind of like move the things around, you see, hey, how does things change as I change variables? That seems to be the common through line for most things. But beyond that, it's going to be based on what your school thinks an investigation should look like. It's a new thing. It's only been around for maybe 2-3 years at this point. But, you've got the resources here to look at, even though I can't necessarily say what your school will do. All right. Anything else? If not, I'll let you enjoy the rest of your day.
Thanks, Chris.
No worries.
Thanks. Have a good day.
You too, mate. No audio. Oh, dear. Oh, well, I appreciate you making it. And, yeah, maybe message me afterwards how you went, or if you're looking to continue. Take care.